Okay, so we were talking about erosion last time. It's part of geology. Geology is affected by gravity. What goes up must come down. And water, of course, is a major driver of geology. 2/3 of the Earth's surface is covered with it. So it's always be a factor in geology over, especially over an extended period of time. Now, a lot of the water, most water is above ground, but some of it's below ground. They're called aquifers. Okay, so there's little cracks in the Earth's in the surface. Water seeps through over time, and eventually you got this huge lake underneath of it. But a lot of people, a lot of communities, they get most of their water from aquifers, not from rivers or lakes, but from aquifers. Particularly got the Oglala aquifer here in the plains areas. Spelling that right. Over a good portion of Nebraska, also Kansas and South Dakota. That is the main water supply for all those farms in the Great Plains. And of course, these aquifers are why so many people are concerned about oil pipelines. Because if an oil pipeline has to cross an aquifer, crossing someone's drinking water, and pipes leak. So that's why people get upset about that. Now you've got the cracks in the surface here where water seeps in. You have the aquifer developing over time. The water is pumped out of the ground usually. Windmills you see on pictures of old farms, that basically was how they pump water out of the ground. Or sometimes if the water's shallow enough, they just dig a well down into it. But the area where water seeps into the aquifer, that's called a recharge zone. And a lot of communities that are very heavily dependent on aquifers, they often have very strict dumping and pollution laws near the recharge zones. Make sure that nothing contaminates the local water supply. Austin, Texas, they're near an aquifer called the Edwards Aquifer, and they have a whole bunch of dumping laws in and around all over Travis County, trying to make sure that the water that the aquifer is recharged, that it's also not contaminated at the same time. You may often have heard of the water table. This is the amount and level of underground water. See, groundwater does move, but very slowly. It can drift along, it can find little cracks in the cracks and move along further. And of course, water is an erosional agent, even underground. It's going to move things along. And of course, you got soil and rock here in your underground water table, but that does move around. But it moves around a lot because of the weight of the water. Because if the water table starts getting low, the upper surface rock and bedrock and even soil can contract around it or expand around it. Now, water sinks into underground caves, leaving carbonate deposits. sometimes the areas you go in these caves, you have this stalactites and stalagmites. That's caused by water dropping and leaving these carbonate salts as it drops. And stalactites are on top. And stalagmites on the bottom. You have a lot of this activity up in northern Arkansas near the Missouri border. The Ozarks got a lot of those same cracks in the surface, so you have a lot of caves which fill in with water, and a lot of times you have this mineral activity because minerals are developing in stalactites and stalagmites. So you go up and along in northern Arkansas, you see every so often these little spots saying explore whatever cave. Some people make a nice little living off that. Now, of course, the process of stalactites and stalagmites, you can kind of determine the age of it by the thickness and of these deposits. But in some areas, the water table is closer to the surface than others. El Dorado is a good example of this. We tend to have a very high water table, especially here in town, because a lot of our water is underwater. We actually have underwater rivers, underground rivers. You may notice some of these different spots here in town where you're crossing a bridge, but there's like a little creek that starts somewhere and then stops. What's happening is that water is going back underground. It goes above ground very briefly, goes back underground. For example, go over to 10th Street, over by the Municipal Auditorium. You've got that little creek kind of runs underneath that bridge that's finally opened after a year. But where does the creek come from? Where does it go? It's not just all drainage water. You go back under 8th Street, back under the baseball fields, there's water running underneath the surface there, part of the water table. But it comes up just close to the surface around 8th Street, goes around a few blocks underneath the 10th Street, then past those apartments and back underground again. And it does that all over town. But that's a part of the water table. Actually, if it's deep enough, it's good to be able to access that water, but sometimes the water is too deep and through too much rock to access easily. Sometimes it's so close to the surface that it kind of seeps up into the ground, making it basically constantly muddy. You also have something called karst topography. It's a large limestone region marked by sinkholes, caverns, and underground streams. You ever heard about, it's often in Florida, they have these huge sinkholes that take up like an intersection or a parking lot or half a city block, whatever. That's karst topography at work. So what happens is, water is an erosional agent, especially around limestone. So what happens is, it keeps working on the limestone for centuries, till eventually gets weak enough, the surface weak enough that a sinkhole forms. The top just collapses on top of it. And of course, caverns, those are part of it. I grew up in Dallas, Texas, and As long as I could remember, there was this sign right off I-30. Carlsbad Caverns, 8th wonder of the world. Next exit, go back 456 miles. I remember that exaggerated number, 456 miles. Go to New Mexico to see these caverns. But that is another example of karst topography. Those caverns have formed. Those cracks in the surface. Now, water, of course, it freezes. We live in one of those narrow little bands around the sun where water can exist in a liquid form on the surface. It's not too cold where it's all frozen, or not so hot where it's all boiled off to steam. It's just kind of that right little spot. But we do have a lot of extremes of weather, which means in areas closer to the poles, ice forms, especially in the winter months. So what happens, you get a lot of ice, you get glaciers. And glaciers, it's ice. It can cut through rock over an extended period of time. Glaciers do a lot to affect the landform of different areas. Now, glacier, of course, is a large body of ice. The thing is, though, water has unusual properties. It's one of the few substances that when it freezes, it expands. So that most substances, when they freeze, they actually contract, become more solid, but not water. And while it is a solid, it can move. Glaciers, they build up over time. The way the ice kind of flattens out and spreads out, kind of like glass. Now, we have to understand about glaciers is they're not built up over one winter. They're built up over many successive winters, thousands of years. So you get snow, and you're in a northern region, that snow doesn't melt in the summer. So the next round of snow that comes in just adds on top of it, top of it, top of it. And you ever tried to save a snowball, put it in the freezer over the winter, of the summer? What happens to it? It turns to ice. Same thing. It's that snow solidifies and hardens into ice. So it slowly moves down slopes or spreads outward on a land surface. And saying glaciers, they've really affected a lot of our geologic history. And of course, these glaciers, they store a lot of water. It's one reason why they're concerned about Greenland. Greenland is basically a solid glacier. You have a few little areas that are little rocks, little bits of a grassland, but not much. Most of it is solid ice built up to a height of about 10,000 feet. Like I said, that's a lot of snow over a lot of time. Well, with temperatures getting warmer, especially in summertime, what happens? That glacier is starting to melt. So you actually have rivers in Greenland now where you shouldn't have those. And so you've got millions of gallons of water dumping into the Atlantic Ocean. Glaciers, they push through over time. I'll give you. So go here, book page 68, see an example of glacier patterns. The top one here talks about glacier patterns, and of course the bottom one here is glacial patterns in the last major ice age about 15,000 years ago. course, flip it over, you get to see the page 69, the different kind of landforms that glaciers can create. Because you can see here on page 68, you got a glacier. It's moving down this mountain valley. What's happening is it moves south and it moves further down and spreads out. It's because the immense weight of this glacier, it's picking up and carrying a lot of rock and dirt with it. So it's cutting through where it's at. So glaciers, yes, very powerful erosional agent. Cape Cod, Massachusetts. You have the little hook on the end of Massachusetts. That was caused by glaciers. Maximum extent of glaciers, thousands of extended period of time ago. The glacier came, deposited a bunch of rock and dirt in this area, creating that little, what was right there. Like I say, we're not talking about just one winter here, or just a couple of winters. We're talking about thousands and thousands of years. At the height of the last ice age, about 40,000 years ago, there's glaciers in New York City that were about a mile high. That's tall, that's very tall. But it took many successive winters and heavy snowfall to build that up. It just didn't just come along overnight. And as it retreats, well, the rock dirt's got to go somewhere, so it's left where it is as the glacier moves back. And like I said, it's very heavy. If you get rid of all the ice in Greenland, what you have underneath is basically this kind of bowl-shaped area. It's kind of flattened and depressed because of the weight of all that ice for so many centuries. And even the Great Lakes, shaped the way they are because of glaciers. As the glaciers add to its mass over time, and a glacier could advance as much as a meter per day. They're slow, but they're steady. Now the Earth, it kind of goes through these natural cycles, but these cycles take tens of thousands of years to run through. Sudden changes in the Earth's climate, like we've been seeing, it's caused by other factors, basically. Sudden increase of the carbon dioxide in the atmosphere, particularly through pollution. Well, why do glaciers form? Well, one theory attributes volcanic dust to periods of atmospheric cooling by preventing solar radiation from reaching the surface. Basically, what they call a nuclear winter effect. And that can cause global temperatures to cool and for glaciers to form over an extended period of time. Now, this is the power that volcanoes have. They can spread dust and debris in the atmosphere that can affect the entire planet. In the year 1816, there was a volcano that erupted in the South Pacific. It spread dust all over the world. In the United States, 1816 is called the year without summer because it was snowing in July. That was how much dust had been kicked up in the atmosphere, causing temperatures to plunge that far in, even in North America. and every so often there's a volcanic eruption. May see for months afterward, for the minor eruption. These very spectacular, very beautiful sunsets. The colors all kind of scattered across the horizon because of volcanic dust. Can have that effect. So the effect can be subtle or it can be extreme. Meteor dust can cause the same effect. For example, 65 million years ago, a meteor struck the Yucatan Peninsula. Kicked up so much dust in the atmosphere, the Earth's surface was surrounded with dust for a long, extended period of time, causing the temperatures to drop and the dinosaurs to go extinct. One meteor impact caused a mass extinction, and these massive glaciers to extend across the Earth's surface. They can mark that event. There's something called the KT layer in the Earth's rocks around the world. It's about 1 million years before present. And you got this layer of this element called iridium, coating the entire planet. KT for the different geologic ages. Cretaceous versus Tertiary period. And all that iridium came from a meteor, which caused dust to block out the sun's rays, causing temperatures to drop, ushering in this era of extinction. And you can see that layer everywhere in the world. Just got to dig deep enough and know where to look. And of course, there are known changes very slight in the Earth's orbit, its shape and tilt, over the last 500,000 years that caused cooling. One theory suggests that when continental plates drift over particular poles, that can cause more glaciers. For example, here, Antarctica. It's drifted over very cold areas, so it's over the South Pole, so it's gotten a lot colder there because there's no warm water or cool water able to go underneath that ice, unlike the North Pole. The North Pole, with temperatures increasing summers, there are a lot of parts of the North Pole area that are ice-free during parts of the summer. And it can do that because there's water underneath it. Go underneath the ice. It's not solid ice from the top of the surface down to the continental plate. No, it's just ice just at the surface. Solar cycles cause this. Some of the Earth's surface wall particularly. But the sun goes through its own cycles. Now the sun, as stars go, is actually fairly stable. It does go through its periodic eruptions of plasma and ionized gas every so often. But not so much it's going to really affect life on Earth here. Not like some would call flare stars, basically just these massive explosions that can cause dramatic increases in light and radiation and suddenly go very dim again. The sun's not that dramatic. Like I said, if it was, life here on Earth would be very, very different. If it existed at all. But the sun goes through periodic cycles of sunspots. Little dark spots on the sun's surface. You can sometimes see them in pictures. Don't look at the sun directly with your eyes. These little dark spots, what they are is they're intense magnetic storms. And What happens when the sun has a lot of sunspot activity is it's sending out a lot more energy. So the Earth gets a little warmer over that period. But other times the sun has very little sunspot activity, so it's not sending out as much energy. Basically not as much turbulence on the sun's surface. So the Earth gets cooler. It's a period called the Maunder minimum. Astronomers in the 1600s, early 1700s found very few, if any, sunspots at all on the sun's surface. The result, temperatures were dropping. Some people call this the Little Ice Age because it just got kind of so cold on Earth for a while. And there was another incident like that earlier during the Middle Ages. So the sun changes its own polarity every 22 years, but goes through these sunspot cycles every 11 years. Now, geologic evidence suggests that throughout most of the history of the Earth has been ice-free. In fact, we're in a period where we have a lot of glaciers. That's actually kind of unusual in Earth's history, as far as geology goes. Actually, human beings really kind of emerged from the last major ice ages. Those last ice ages caused a lot of changes for humanity. One thing, human beings able to go from Asia into North America. That's the ancestors of the Native Americans. Like I said, permanent settlements and the domestication of agriculture come along about 12,000 years ago, just a couple thousand years after the last major ice age ends. It prompted a major change in human activity. Now, continental drift, it can cause temperature extremes, a very slow process. Remember, we're talking about a process over millions of years. These continents moving back and forth, that can cause a lot of shifts in global ocean current patterns. And ocean currents, those really do have a lot to do with the weather. Then we got the Gulf Stream off the Atlantic coast. That carries a lot of warm water up north towards Canada and even all the way to Ireland, helping give Ireland and England, even parts of Western Europe, fairly mild winters. Well before Europe and North America were joined millions of years ago, you don't have a Gulf Stream because you don't have an Atlantic Ocean. So weather patterns were very different. But today you have continent-sized glaciers. Over Antarctica, Greenland, Baffin Island, that huge island just off of the coast of Canada by Greenland. 10% of the land area on Earth is under ice. The Greenland Great Glacier is part of a larger glacier covering parts of northern North America. Like I said, depths up to 10,000 feet in some areas, thinner in other parts of Greenland. But here's an interesting thing about it. These glaciers is, as they freeze, the snow comes down, freezes, it traps tiny little air bubbles inside of it. So you can actually drill down into glaciers and you can find samples of air that are tens of thousands of years old. And that's very useful for scientists. called ice cores. From these ice cores, you can find what is in the atmosphere at those different time periods. Sometimes samples of pollen, but also what is the level of carbon dioxide in the atmosphere. Further up you get to the surface, the more recent it is. And what we found through these ice core samples is in the last 200 years, basically, since the beginning of the Industrial Revolution, carbon dioxide levels have dramatically increased in the atmosphere. Again, because of industrial activity, all those factories spewing out smoke and everything else that is added into the atmosphere. Like I said, the last major ice age about 15,000 years ago. Again, the one creating the land bridge between Siberia and Alaska. Another ice age about 40 to 50,000 years ago did the same thing. Now, you also have an effect called permafrost. It's an area that is permanently frozen earth. It can be as much as 1,000 feet deep. Actually, it's not necessarily ice on the surface, but basically everything's just frozen. Especially given this above the Arctic Circle, below the Antarctic Circle. Areas where you don't have a lot of vegetation because everything's basically still frozen. But not necessarily covered in glaciers. The weight and motion of glaciers breaks up rocks and scours the lands that they move. So you got such a thing as what's called glacial trough. It's a deep U-shaped valley dug out by glaciers. Example, what you'd see here in our examples, it moves down a mountain. That would an area be called a glacial trough. You have fjords. Norway is very famous for it. It's got that kind of craggy surface here where it kind of goes and keeps going like this. That's caused by glaciers. It's in the land. Over many ice ages, these fjords were formed. Basically, the glaciers cutting into the rocks, creating all these. Got these very high mountains, but also you have these little inlets here and there, with little bays and so forth. And that's why you had the Vikings, because to get from one point to another, they had to go by boat from one fjord to another. It's actually a Scandinavian word. And yeah, these are glacial troughs underwater. You see them in Norway and in British Columbia. Glacial till. That's the landform left by deep deposits of sediment for glaciers, usually in an outwash plain. So, these are glaciers. Cutting and forming different landforms. Actually, I can do all sorts of weird things over time. Example, in Central Park in New York, an unusual kind of landform they found was in some of the rocks in Central Park, there are these very shallow grooves on some of these rocks. What are they caused by? Glaciers. Pushing rocks down on these rocks, basically cutting these little troughs in them, or extended period of time. Yes, glaciers, they do have a tremendous amount to do with our climate and, of course, our topography.